Hello, welcome to Vedil Vagaparai. In this video, we are going to see a reaction based on osmium tetroxide. And this particular reaction is a very interesting reaction. We will see the details of this reaction before we discuss the question. So the question is taken from IIT JAM 2025 question paper. So the question is, an organic compound P6C8H16 produces a meso compound upon oxidation with osmium tetroxide slash NMO. The compound P is NMO is nothing but N-methyl morpholine N oxide. So what is so special about NMO? Why is it being specially mentioned? These are the things that we will see. And then in this question, they have asked what is the organic compound. So they have given 4 options and they are asking us to tell us which among these 4 options will give a meso compound as a product on oxidation with osmium tetroxide. So first we will see the basics of this particular reaction, then we will discuss this question. So what is this osmium tetroxide? So when you see osmium tetroxide, it's a very expensive, highly toxic volatile liquid. And because it can undergo reaction with alkenes very swiftly, it can affect the eyes. It can cause blindness when exposure to this particular vapors are happening. And so the best way to, because of its expensiveness, the best way to carry out this reaction is to make use of catalytic amount of osmium tetroxide so that we don't lose the reagent. In the sense, the reagent is regenerated as and when it is converted to the other product. So the catalytic amount requires only 1 to 2 mole percentage, and then it is taken in stoichiometric amounts along with that of a reagent which is a co-oxidant. This co-oxidant will not oxidize the alkene, it will only oxidize osmium 6 to osmium 8. So the co-oxidant that is used is N-methyl morpholine N oxide. So N-methyl morpholine's work is to convert osmium trioxide that is formed to osmium tetroxide. That is, here osmium is in oxidation 6 state, so it is converted to oxidation 8 state. So this conversion is mediated by NMO, and that is the reason why the addition of this reagent is very important. So in the absence of this reagent, what will happen? We will have to take equimolar quantities of osmium tetroxide because osmium tetroxide will be used up in the reaction. So when you see the reaction is a simple addition of 2 hydroxyl groups across the double bonds. So alkenes are converted into dihydroxy compounds or diols, and these diols add from the same side. That is why they are called as vicinal diols. And because it is adding from the same side, it is called as syn addition. And we see because it is a concerted reaction and it's an addition reaction, cyclo-addition reaction, it involves 3 species of the osmium tetroxide and the 2 carbon atoms of the alkene. And so it is a kind of 3+2 cyclo-addition reaction. And at the end of the day, we get vicinal diols. And the reason for the vicinal diols being formed is because the oxygens of the osmium tetroxide are added from the same side. So that is the reason why we get vicinal diols. So this is a very highly, in case of a stereochemical starting material, a product formation, this is a very important understanding. So now this particular reaction where we are making use of NMO is called as actually Upjohn dihydroxylation. So this reaction of osmium tetroxide with alkene in the presence of NMO is actually called as Upjohn dihydroxylation reaction. It is named after the not the scientist but after the company to which the scientist belonged. So it's very interesting. So here there is this cyclic scheme shows us how osmium tetroxide reacts with the alkene to form the intermediate, and the intermediate then results in the formation of the diol and resulting in osmium in +6 oxidation state. This is in +8, this is in +6 oxidation state. So NMO then is used as an oxidant and then converts to osmium tetroxide with the formation of a oxidized product. So this oxidant is oxidizing only osmium tetroxide, and osmium tetroxide is oxidizing the alkene to a cis diol. So now let us go back to the question. So in the question, we will first write down the structure of all these organic compounds: E4-octene, Z4-octene, E3-octene, or Z3-octene. So we see that these are the structures of the octenes. So when we see the structures of these octenes, what is said, they on oxidation forms a meso compound. We know that when osmium tetroxide reacts, it reacts by syn addition. So the two R groups, if they are trans to each other, they will be in the opposite direction on the adjacent carbons. So now when we see the 4E octane, the R groups are trans to each other, like what is here. When it is Z, the R groups are cis to each other. Whereas when we talk about 3 octane. In 3-octane is an unsymmetrical molecule. So because it's an unsymmetrical molecule, definitely there is no possibility of getting a meso compound, because we know in stereochemistry a meso compound is one which has a plane of symmetry which gives internal compensation. So when it is 3-octane, internal compensation is not possible. So that is why we will ignore these two options. We will only look at the option option A and option B. So in case of option A, we see we get this as the product, like what we have represented here, and option B, we get it like this because both the R groups are on the same side. So when we look at these two molecules, it is very obvious and clear that when I draw a line through the molecule, we see there by way of internal compensation, only the one which is formed from 4-octene, Z4-octene, will be a meso compound, whereas the one which is formed from E-octane will not be a meso compound because the groups are opposite to each other. Whereas here the groups, all the groups, the OH groups and the CH3R groups are on the same side. So the correct answer is B, which is Z4-octene. This is the correct answer. This is the one which will give the meso compound. Thank you. Like and subscribe to our videos.